All right. So today we shall be discussing about the petroleum traps. It is a very important concept. So before beginning, let me just tell you that we had seen in the petroleum system the source rock. So the source rock is the one where the hydrocarbon gets generated. Then comes the reservoir rock, where the hydrocarbon gets accumulated. Now imagine that there is a source rock. So I had also told you that in some cases the source rock itself acts as the reservoir rock, and in some other cases the oil migrates from the source rock to the reservoir rock. Let us imagine that this is a source rock, and overlying the source rock there is the reservoir rock, like this. So this is the reservoir rock. Okay, so now what happens is that, as I had told you, that oil, it migrates from the source rock to the reservoir rock. But imagine that there is no mechanism of trapping that oil or trapping that hydrocarbon in the reservoir rock. So what will happen? It is a volatile substance. The way it moves from the source rock to the reservoir rock, similarly, it may move out of the reservoir rock as well. And let us say that you are an oil company and you are going to drill over here, and you see that in your analysis and exploration methods you were finding that there was oil over here, but it has moved away. Why? Because there was no such trapping mechanism. There was no sealing mechanism, because for a rock to be called as reservoir rock, two things are very important. What are they? Porosity and permeability, which means that the reservoir rocks need to be porous and permeable so that they can allow the extraction of hydrocarbons. Now, since these rocks are porous and permeable, it is quite possible for the hydrocarbon to even get migrated from the reservoir rock as well. So, reservoir rock may lose the hydrocarbon if there is no trapping and no sealing mechanism. For that, the petroleum traps are very important. When I say petroleum, I am talking about both oil as well as gas, so don't get confused. So the hydrocarbons, they need to be trapped in the reservoir rock. And how are they done? They are done with the help of traps as well as the seals. So let us see what the traps are. So going by the definition, the trap is any geometric arrangement of rocks. Keep this in mind, that a trap need not be having the same age as the reservoir. It need not be having the same type of lithology as the source rock. So it is basically a geometric arrangement. When I say geometric arrangement, you should now guess that we are talking about the folding of rock or faulting of rock, or the structures formed by the various mechanisms. So any geometric arrangement of rock, regardless of its origin, that permits significant accumulation of hydrocarbon in the subsurface. So what does it mean? It means that if there is any structure, it could be the structure of reservoir rock itself, no problems with that. It could be the structure formed by some other mechanism which may not allow the hydrocarbon to escape the reservoir rock, like a fault. So these are the structures, the geometric arrangement which allow the significant accumulation of hydrocarbons. If such structures are not there, it is very easy for the hydrocarbon to move from their place of accumulation and you may lose the hydrocarbon. That makes it a very essential component of the petroleum system. And remember that the simplest type of traps are represented by anticlinal structures. So when I say that the simplest type of traps, whenever people go for the hydrocarbon exploration, the first thing they try to search in the seismic maps is this convex upward structure, a structure like this, like this. So if they find this in the subsurface, then they concentrate themselves on this structure and then try to do the further studies. So why this is the most sought after structure, we will just see. You must have read in the structural geology class how these anti-formal structures are formed. So basically, if we are looking at a simple anticlinal trap, then look at this diagram. This diagram has several parts of it which are very beautifully explained in this. Normally, when we are talking about the presence of liquids or fluids in a rock, the fluids could be of three kinds. It could be water, it could be oil, or it could be gas. And in this diagram, you can see all three which are shown over here. Now, let's look at it one by one. The crest or the culmination point is this. This is the highest point of the trap. Okay. So, this is called as the crest. You all are aware, crest and trough. So, the crest is the highest point of an anticline, and then the trough is the lowest point of a syncline. Then closure. This word closure, what does it mean? It is the vertical distance from crest to the spill point. And what is spill point? It is the lowest point at which hydrocarbon may be contained in the trap. So in this trap, in this structure, the hydrocarbon or that fluid, it may not be held beyond this point. मतलब इसके नीचे आपको हाइड्रोकार्बन नहीं मिल सकता. That is called as the spill point. So the vertical distance between the crest and the spill point, it is called as closure. Remember, closure is very, very important. If you do not have the adequate closure or the tight closure, again the hydrocarbons might migrate. Then the edge water. You see this edge water. What is edge water? It is the zone of reservoir laterally adjacent to the trap. So there are two. So in the reservoir where the to the trap, this water zone which is laterally adjacent. See, this is the water zone and this is laterally adjacent to this trap. Okay, this is called as the edge water, water lying on the edge. Then what is the gross pay? Remember, we have two words, gross pay and net pay. So what is the gross pay? Gross pay is the vertical distance from the top of reservoir to the oil water contact. So here we are seeing, since we are interested only in hydrocarbons, so when we talk about the gross pay, we are interested in knowing what is the amount of hydrocarbon contained in a certain reservoir which is being held by this trap. So if you look at this right hand side over here, this is the oil water contact over here. So we are not interested in talking about the water. So we are more interested in talking about the oil and gas. So over here, the hydrocarbons, this is the gas plus oil. We are aware that water has the highest density, so it will be at the lowest, followed by oil and then the gas. So the oil water contact, it is called as the, from the crest to the oil water contact, it is called as the gross pay, the total pay. Okay, and immediately below this oil water contact, you can see there is the bottom water. So the zone immediately beneath the petroleum, this is the simplest type of trap, and this diagram has been taken from the book Essentials of Petroleum Geology by R.C. Shelley. Then you may have, so this is a normal anticlinal structure. Okay, but you may have monoclinal dips as well. So here, if you see over here in this case, on the monoclines, here the structural relief, in this case, in the first case, the larger diagram, in the anticline, the closure of the trap is same as the structural relief. And what is the structural relief of this trap? The structural relief of this trap is from the crest to the spill point. So this is the structure. So how much convexity this is showing, it is called as the structural relief. Does that structural relief coincide with the closure? Yes, here we can see that in the normal anticlines, you can see that the closure is coinciding with the structural relief. But in case of monoclinal dip, where you can see only a part of the fold, here this is the structural relief, but closure is only this much, because here only in this zone the hydrocarbon may be properly held. This is called as the closure. So if any question is asked that in which type of folds or in which type of traps you will not find the closure same as the structural relief, answer will be the folds with the areas of monoclinal dip. So this is the general diagram of a simple anticlinal trap. Okay, here you saw the gross pay, which was the vertical distance from the top of the reservoir. So here in this case, this is the gas plus oil. What is written over here? This is the reservoir. And then the oil water contact, this is OWC. OWC is oil water contact. So in the OWC, you can see the entire hydrocarbons, the gas plus oil. This is called as gross pay. But like we get our salaries, somebody may have a salary of rupees 1 lakh, but what he gets in his hand may be lesser, because he might have to pay taxes, he might have to pay the rent or HRA, he might have to pay for some of the loans he must have taken, like that. So the net pay may not always be same as the gross pay. So gross is the total, net is what you get in the hand. Similarly, in case of hydrocarbons, you can see that there may be, suppose, X amount of hydrocarbon, but depending on the structure, depending on the conditions of the oil field, depending on the properties of the reservoir rock, it is not possible for us to extract the entire oil. So the amount of oil which is extracted is normally less than the amount of oil or hydrocarbons which is contained in the rock. So in this diagram, you can see that from the top of the reservoir to the oil water contact, which is the deepest level of producible oil, this is called as a gross pay. But here you can see that the oil bearing strata, the oil bearing horizons are intercalated with some other lithology. So you will not be able to, so let us suppose that you put a drilling rig over here, sorry, here, and this is your well. This is your well. So do you think that you will be able to extract the entire oil? Because this zone is a barren zone, this zone is a barren zone. So the amount of oil which you are able to extract from this gross pay, it is called as the net pay. Okay, so all of the gross pay does not consist of productive reservoir. So gross pay is usually different from the net pay. And what is the net pay? Net pay is the cumulative vertical thickness of a reservoir from which petroleum may be produced. So in this type of reservoir, you can see that the net pay is the producible part of the reservoir. The producible part, because here from this part, I'll just show you. In the top one, you are able to see this is a productive zone, but what about this? Here, this is all oil here as well and oil here as well, but this part may not be extracted. Then again, this is oil here. Okay, so you just saw this difference between the gross pay and net pay. All right. Now, oil water contact, as I have told you, it is the deepest level of producible oil. Okay, so the trap, in a trap, oil, gas, or both may be present, as I have told you. And the oil water contact is the deepest level of producible oil. Similarly, there can be gas oil contact or gas water contact. So remember that the OWC is not necessarily present everywhere. If in some reservoir there is no oil, only gas, then you may get a gas water contact. If all are present, say gas and oil and water, all three are present. So here if you see, this is gas oil contact over here, this is oil water contact. But let us suppose that this is only gas, so this OWC will become GWC, gas water contact. So as the case may be, the contact between the hydrocarbon and water, they both will be the deepest level of producible hydrocarbon. Okay, so the gas water contact will be the deepest level of producible gas. In the same trap, as I have told you, the gas overlies the oil because it has a lower density. So the presence of oil and gas, now whether the oil and gas both will be present, it will depend on the chemistry, what type of kerogen is involved and the level of maturation. So is the rock reaching into the oil window or gas window of the source rock? And then of course the pressure and temperature. So chemistry, maturation level, pressure and temperature, these are important to decide whether the rock will be having oil and gas or only one of them. Okay, now the boundaries between oil and gas may be very sharp or maybe gradational or transitional. That we'll see depending on what type of trap are we going to look at. Now the abrupt fluid contacts, they indicate a permeable reservoir. Remember that one, if the reservoir is permeable, then the the fluid contacts means the gas being lighter will go to the topmost layer, then then will come the oil and then the water. So there will be a very clear cut distinction between the oil water contact, gas oil contact. Okay, but if it is a gradational reservoir, means it is a gradational contact, so you are seeing that slightly the oil zone is entering into the gas zone, the water zone is entering into the oil zone. So here the permeability is lesser, and once the permeability is less, then the capillary pressure will be higher and that will push the liquid in intruding into each other's zone. So this contact is decided by what is the permeability of the reservoir. Okay, so let us now come to the classification of traps. This is a very important question in all sorts of examinations of geology, whether it is GSI, UPSC, whatever. So we have two major genetic group of trap. When I say genetic group, means how they are formed. Structural traps and stratigraphic traps. Of course, there are several more types of trap, but at your level, you are good enough to know about these two major genetic groups. Then the third group, which is called as the combination trap, it is the combination of both of these, whether it is a structural trap or a stratigraphic trap. So as the name suggests, structural traps are those traps whose geometry was formed by tectonic processes after the deposition of the beds involved. Means it is a post-depositional feature. Post-depositional. So once the rocks are laid down, they get lithified, they turn into rock and then they get folded. So the structural traps are caused by folding and faulting. This is the most common type of trap. So here you can see that here the reservoir rock gets folded. This is the reservoir rock and this is the hydrocarbon accumulation. This is hydrocarbon. Over here, this is the hydrocarbon. So they may get folded or faulted, and the part of the reservoir which is holding the hydrocarbon, it gets trapped. Another group of traps is caused by Diaphys. We'll see, this is a very important type of trap, Diaphys. Now, I think it is a Greek word or Latin word, I'm not sure, but the diapir means to pierce. Pierce. Suppose that this is any overlying sediment over here, and the structure from beneath, it pierces into this structure, these sediments. This is called as diapir. So this diapir, which is normally salt and mud, it moves upward. We'll see why it moves upward. And then what it does, it forms a dome-like structure over here. And then if any reservoir rock is over here adjoining to this diapir, it forms a hydrocarbon trap. Now, remember this, that structural traps are formed by the tectonic processes. Their geometry is post-depositional tectonic process. But the stratigraphic traps, their geometry is formed by changes in lithology. When we talk about stratigraphic traps, the most common stratigraphic traps are unconformities. By going by the definition of unconformity, unconformity is a erosional or non-depositional surface where the change in the lithology may be perceived in the field very easily. So the stratigraphic traps are those where the geometry is formed by changes in lithology. They may be syndepositional while deposition is going on, or the post depositional. Both these are quite possible in the stratigraphic traps. Next type of trap is a hydro. So here you can see in the unconformities structure, you can see this is an angular unconformity over here. You can see hydrocarbon which is trapped over here. This is again an angular unconformity beneath the unconformity surface. So this is the unconformity surface, the corrugated one, the undulated surface, and this is the hydrocarbon. So this is again a trap. So this is a type of stratigraphic trap. And then the combination trap, you can see fold and fault. Sometimes they are fault generated folds. We'll see how the fault generated folds are formed. So if they both are occurring together, then this could be a combination fold fault, and sometimes it may be a you know, an unconformity associated with some type of folded structure, that is also called as a combination trap. Next type is the hydrodynamic trap, where the downward movement of water prevents the upward movement of oil. So if let us say that in this type of a structure, the oil is moving this way and the water is moving over here, water being denser, it will block it and it will not allow this oil to migrate. That is called as a hydrodynamic trap. So this is the general classification of different types of traps. And take my word, if you are sitting for the GSI exam, this question is bound to come, a question on the petroleum traps. Okay, so let us now look at the structural traps. This is a very common and simple diagram. You can see that these are the anticlinal folded structure where the hydrocarbon is preserved, or it is trapped in the reservoir rock. And and interestingly, an overlying shale, impermeable shale layer is there. So what will happen? Let us imagine that this is an anticlinal structure and it is having hydrocarbons in it. So let me just draw this black colored, it is gas, and then we get oil over here, which is I am drawing by this blue color, like this, oil. Now this is, and this is all, of course, this is water. Water. Now imagine that there is no rock. So you can see here impermeable shale clay. What it does, this, if this is a reservoir rock, it is bound to have high porosity and permeability unless there is a seal, an impermeable layer which is over here, which does not allow the hydrocarbons to migrate vertically. If it doesn't allow, sorry, if it doesn't allow this to move vertically, then this is called as a seal rock. So what are the properties of seal rock? It has to be a fine grained impermeable layer. So best example of seal rocks, they are shales, clay or gypsum. All these, what do? They seal the trap so that this gas and oil may not migrate further from the trapped area. So the traps which are formed due to folding, the structural traps, they are formed as a result of folding and faulting. The most common type, as I have told you, is anticlinal structure. Now, this anticlinal structure, it is important in the sense that you all are aware that in the anticlines, the hinge area is the one which has got maximum pressure. Maximum stress is over as at the hinge area. So the oil and gas, they migrate and they get trapped in the hinge area of the anticline. So anticliner or fold traps, they can be formed by the compression process, which is formed by the crustal shortening, and they can be compactional anticlines, which is crustal tension. So crustal shortening means you are pushing the rock from both the sides. So if let us say that this is a rock and it is being pushed from both the sides, then it is called as the compression, and the rock may get folded like this. Okay, this is called as the compressional anticline. And if we have a rock and it is being pulled from both the sides, then what will happen? It may undergo faulting, and then you get a horst and graben like structure. This is called as crustal tension. So the anticlinal traps caused by compression are most likely to be found in the subductive troughs, where there is a net shortening of the earth crust. Net shortening means the crust is being folded, and in these fields, in such traps, they are found adjacent to mountain chains of the world, because you are aware that whenever there is a mountain building process, the strata gets folded. While due to crustal tension, what happens? Once the crustal tension happens, which causes a sedimentary basin to form, the floor is commonly split into horst and graben structures. So once the horst and graben structures are formed, so like this, all these are due to the, so this is horst and this is a graben structure. Now what will happen? Let us say the sediments are getting deposited like this. So once the sediments get deposited, you will see that they are now taking the form of a fold, and this is a fold which is generated by the crustal tension. So you can see over here there is a sedimentary cover. This is the basement. These are the horst and graben structures which are at the basement, and you can see how the strata gets folded. So if there is any reservoir rock over here, it will lead to the formation of the trap. So this irregular stratigraphy, which is filled in by the initial phase of deposition, causes the formation of the trap. So the anticlines may occur in the sediment cover above the deep-seated horst. So this is the anticlinal structure. All these are anticlinal structures formed in the areas where there has been crustal tension. Okay. So these are the two types of anticlinal structures: the compressional anticline, which is formed by the compression, which leads to the formation of a fold, and then crustal tension, where the deposition over the deep-seated horst, it causes the formation of anticline. So remember this, that the compressional anticline and compactional anticline, they both may lead to the formation of petroleum traps. Now, when we talk about the faults, so faults, you all are aware that the faults are of different types. So it could be a normal fault, it could be a strike slip fault, thrust fault, and growth fault. Now, how does the fault cause the formation of trap? Let us say that this is a strata which is a reservoir. Okay, so it has some hydrocarbons in it over here, and then in due course of time, due to the tectonic processes, there occurs faulting like this. Okay, so you have strata above it, beneath it, like this. So as a result, what will happen? You will have a fault plane, this strata, then you will have the oil bearing strata, and then again the underlying lithology, like this. And then once the faulting occurs, there will be a slip, and this may cause structure like this. So you have the overlying strata, then you have the oil bearing strata, and then you have again the underlying strata this way. So this was the hydrocarbon. So what is happening over here? Then you have some other new lithology coming up. So this black colored strata where you can see the presence of hydrocarbon. Now this hydrocarbon is trapped by this fault plane itself. Okay, this is what is written over here, that the fault plane must have a sealing effect. So it functions as a fluid migration barrier. The migration problem of petroleum or hydrocarbons is a very common problem in the reservoir. So this oil over here may migrate to somewhere else unless it is either folded, or if it is faulted, then this fault plane, it will seal the hydrocarbon here only. This becomes a trap. So the normal fault, they're commonly associated with graben or rift structures. So in this diagram over here you can see that this fault plane where the slip has taken and it's a normal fault, this is the zone of hydrocarbon which is trapped. We don't know where the down thrown side has gone. In the case of strike slip fault, so these may not be sealed because strike slip fault over here, so this is the type of strike slip fault where they move laterally. But if it is a basement controlled strike slip fault, they produce good anticlinal structures in soft overlying sediments. So here we get a type of combination trap where the fold and fault, they are in combination. The thrust fault, which is a reverse fault, it is due to the compressional tectonics. So you can see over here that this is a fault plane and there has been the down thrown side has gone up, and this has caused the trapping of hydrocarbons not only by fault plane but also by the associated folding of strata. So here this is a fault related fold where due to the reverse movement, the overlying strata has been folded in form of anticlines. Then we get growth faults, a very important type of growth faults which are formed in sediment that are deposited rapidly. So once there is a rapid deposition of sediment, then it grows, there is a kind of slippage of the sediment. So what happens over here, you can see this yellow color line, it is a growth fault, and then you can see some rollover anticlines. You can see some of the faults which are in the same, so if the faults are in same direction as the growth fault, they are called as synthetic fault. If they are in the reverse direction, it is called as antithetic fault. And the anticlines which are associated with this growth fault, they are called as rollover anticline. So you can see a several lot of these sedimentary structure of the structural traps which are formed over here, and this will cause the formation of the hydrocarbon or oil traps. So with the growth faults here, there are several structures associated, not only the growth fault itself but the synthetic fault, antithetic fault, and rollover anticlines. So all these structures, they lead to the formation of oil trap. And how the growth fault is formed? It is formed once there is the differential load of the overlying sediment. It is being deposited very rapidly and then it slips due to its load. This is called as the growth fault. Now depending on the theoretical, the slip of the fault. So let us see what is the slip. If this is a strata, it gets faulted. So now if this is the fault plane, FP fault plane, so how much it has come down, the net slip, okay, the direction in which the rock goes, the part of the rock goes down, that is called as the slip. Now it is very very important that the fault should be enough, the slip should be enough so that the fault plane closes the rock. So for example, I'll just show you that if this is the reservoir rock with the reservoir in it, with the oil in it, there is a faulting, and due to this faulting what happens is, and slip is not more, and this is how the slip of the rock happens. You can see that there the closure is not complete. So all these hydrocarbons may easily migrate from here because fault plane is also a plane of weakness. So it may allow the migration of this hydrocarbon to this other part, the down thrown side, because it is a porous and permeable rock. So closure becomes very, very important. So there are 8 theoretical geometries for fault traps, assuming that the fault do not separate the juxtaposed permeable beds. Means, let us say that the permeable beds, they are not sent too far away due to the faulting. So what will happen? You can see here that when the dip is, dip with the fault, it is in the direction of the faulting. So what will happen over here in case of a normal fault? If this is the hydrocarbon trap over here. If there is a sufficient slip, then there would be an unlimited closure. Means this hydrocarbon will be trapped by this fault plane. If the throw, if in technical terms, if the throw of the fault is more than the thickness of strata. Okay, so what is the throw? The vertical movement in a fault. I am sure you all are aware of the terminologies associated with faults. So if the throw of the fault is more than the thickness, then there will be unlimited closure, as the hydrocarbon bearing portion of the rock will be sealed by the fault plane. But if the throw of the rock is less than the thickness, then there will be no closure and this oil may easily migrate. So this will be the uh, that portion of the rock may remain connected. So there will be no closure at all. Now, in case of reverse fault, in the same way, when the dip is with the fault, then in case of reverse fault, again, once the throw is more than the thickness, you can see here, this is a beautiful diagram which shows unlimited closure, means a very good trap. Closure has to be there for the hydrocarbons to remain in their place. But if it is the other way around, the throw is less than the thickness, then there may be a spill point and there is a limited closure. So there are chances that the oil may or may not migrate through that spill point. Okay, but once the dip is against the fault, here you can see that the dip of the rock is in the direction of the fault, here they're against the fault. So here again, once the throw is more than the thickness, then there is unlimited closure. But if the throw is less than the thickness, in case of dip against fault, okay, dip against fault, there is possibility that in normal fault you may get limited closure once the throw is less than the thickness. While in case of reverse fault, once the throw is more than the thickness, of course there is unlimited closure. But if the throw is less than the thickness, is in case of reverse fault, there is no closure at all. So you should remember this diagram, which tells you that in case of the fault traps, such conditions may occur given certain prerequisites. So normal faults which have the unlimited closure once there is the throw more than the thickness. So remember that if a question is asked in which of the following conditions the unlimited closure is possible in the normal fault, and if you see that throw is more than the thickness of the rock, then 100% there will be unlimited closure, whether it is a normal fault or a reversed fault. But in case where there is the throw is less than the thickness of the rock, in case of normal fault there will be no closure, while in case of reverse fault there will be a limited closure, and likewise. So I hope this makes this diagram very clear, this explanation. Okay, so this completes the structural traps. Now let us see the diapiric traps. As I told you that the word diapir means to pierce through. So normally what happens is that the upward movement of sediments that are less dense than overlying sediments, it happens. But remember that there are certain conditions and ways in which these sediments, it may, you know uh, they push through the overlying sediments. So what happens, see, this is a map, seismic map, wherein you can trace out a diapir. What is happening over here, and this is a common diagram where you can see how the diapirs, they lead to the formation of the traps. So here what happens is that normally the the diapiric traps, they are formed either by the salt flats or by the underlying shale. So salt, we will see how these are formed, but just let us look at this. So in this situation, the sediment tend to move upward and may form diverse hydrocarbon trap. They are not normally regarded as true structural trap because they are not formed by tectonic forces, except in a few cases. Normally, the diaphoric traps, they are not formed by tectonic forces, rather by the compaction and the burial depth of the sediments. We'll see. Similarly, they are also not initiated by stratigraphic process because there is not the change of lithology. It is just the underlying sediment which has got lesser density. It pushes through the overlying sediments. So these traps are generally caused by the upward movement of salt or overpressured clay. So let us see how the upward movement of salt happens. Salt is much denser. Remember, it has a density of about 2.03 gram per centimeter cube. Now let us see that this is a salt flat, you know, this is salt, and it is being overlain by other sediments. Unless and until these sediments are either on the surface or they are shallow in their burial depth, they are less dense. These sediments, they are less dense. And what are these sediments? Normally sand and clay. So sand and clay are less dense than the salt once the burial depth is less or they are on the surface. But as the depth of burial increases, as they start going down, what happens is that compaction occurs in these sediments, which causes loss of porosity, and slowly their density rises density rises. What happens now? So you can see this plot. It's a beautiful diagram which shows that the salt, which is this vertical line, it is 2.03. This is how the density increases. Remember, it's reverse direction. Here, this is how density increases. So the clay and the sand, they have much lower density at a depth of almost 800 to 1200 meters. Now, less than 1 kilometer depth, the density of the the density of sand and clay is less than the salt. But at a depth for 800 to 1200 meters, this density suddenly starts to increase. So you can see that beyond this burial depth of 800 meters, the salt, it gets less dense than most sediments, and therefore now the salt becomes less denser. Once the salt becomes less dense, then the salt starts its movement upward. It pushes itself through, and once this happens, the salt diapir, it comes up. So what will happen over here now? The adjacent strata, now they start to get folded like this. You can see very well, like this. So this was the sediments which were earlier less dense than the salt. Now their density has increased due to compaction, and by chance, if any of these strata is a reservoir rock, then this is the oil trap. So this trap is formed by the salt diapir, which was basically a denser layer, but due to compaction at a depth of almost 1 kilometer, the salt becomes less dense, pushes itself up, leading to the formation of these anticlinal structures, which is also called as drape anticline, or these structures which just pinch out over here on the boundaries of this, and they form a trap. This is also a very important type uh, of the trap. Now, once this pushes itself up, then you may again see the formation of some types of the structural traps because of the folding of the strata. Now, in other instances, now this is the normal vertical movement of salt, but sometimes movement is apparently random. in some salt structures which may not pierce through completely. If the salt structure is not piercing through completely, then overlying strata are only updomed, means that if this is the strata and this is the salt layer over here, if it is unable to pierce it completely, then this strata may get folded like this. This is one type of trap. And in others, so this is here, you can see that this structure is only updoming structure, which we also refer to as the domal traps, while in this case here the salt has pierced completely. So this is a type of pinch out trap, this over here. Now what happens is the salt movement. What is the salt movement called as? It is called as halokinesis. It plays an important role in entrapment of oil and gas by this type of movement. So you can see several kind of traps over here. So this A, it is the domal trap. B and C, they are fault traps. You can see just because of this piercing up completely, the strata may get faulted, and due to this fault, they are the traps are available with unlimited closure. Then D is the pinch out trap. You can see that this strata was like this, but now due to the piercing completely of this, so how this pinch out will form? Imagine that this would have completely pierced over here, then this strata would also have been forming the pinch outs. So what is happening over here is that it is simply pinching out against the wall of this salt diapir. And then F is the truncation trap. You can see just because of not completely piercing it, the oil bearing strata truncates over here. It finishes over here, it stops over here. So this is called as a truncation trap. So you can see that how complex this process is, that you can find several of such structures being formed by the salt diapirs, which lead to the formation of the different traps. All right. Now let us come to the stratigraphic traps. As I had already explained you previously, that these are due to changes in lithology. Such changes may be caused by the original deposition of rock, as with reef or channel. Alternatively, there may be a change in lithology post-depositional. So there can be a syn-depositional change, post-depositional change. Now, these stratigraphic traps are largely classified into two, which are one which are associated with unconformity, the other which are not associated with unconformity. The ones which are not associated with unconformity, they are depositional or diagenetic in origin, and the examples are pinch out, channels, bars, and reef. And then there are also the traps which are due to the porosity and permeability changes. While the ones which are associated with unconformity, if let us say that this is the unconformity surface, if it is formed above the unconformity, it is called as it is called as supra unconformity. If it is formed below the unconformity, is called as sub unconformity. And these two can be classified as on-lap, strike valley, or channel, and then there could be the truncations as well. So these are the different types of stratigraphic traps which are important for the accumulation of oil and gas. Okay, so let us now look at the primary or depositional stratigraphic traps. So here you have the lateral depositional changes, where the facies, you can see that the facies are changing laterally. They are changing, there are two different facies which are changing. And this dotted one, this is the hydrocarbon accumulation. So here you can see that all these diagrams are from the book by R.C. Shelley, The Elements of Petroleum Geology. So the traps which are created by lateral changes in the sedimentary rock during deposition. So these are all syn-depositional changes. So here you can see that juxtaposition of a reservoir and seal caused by lateral. So this is a seal rock and this is a reservoir rock. So what is happening? The seal rock, which is impermeable, is sealing this hydrocarbon. It is not allowing this hydrocarbon to move, and therefore the seal rock, which is laterally adjacent to the reservoir rock, acts as a barrier for the fluid migration. Then Pinch outs. So this is the porous permeable unit where the hydrocarbons are accumulated, and they simply end into a non. So this is a impermeable unit. Impermeable. So what are happening over here? This pinch out, it will be blocked by this impermeable layer, and there will be no fluid migration. So both these, the facies change and depositional pinch outs, they are the examples of the syn depositional. So the traps which are formed by the uh, ongoing sedimentations. The second is the trap formed by buried depositional relief. So here what is happening, that there is a reef structure on which the uh, you know the sediments are getting buried, and they form the traps. So here you can have a reef, you can have an aeolian dune, and you can have submarine fan lobe, where the depositional of or the porous and permeable strata, which is the reservoir, may be sealed by the overlying or laterally adjacent impermeable strata. And how does this happen? You know, the sedimentary process, they form a trapping geometry but require burial by younger impermeable section. So this could be a this could be an older permeable section which is overlain by a younger impermeable section, and they may form the trap over there. So the primary depositional stratigraphic traps, you can see, as I had just explained, that there are two general classes. So these are created by changes in the contemporaneous deposition, and they are not associated with significant unconformities. They are not associated. So the facies change and depositional pinchouts, these are the ones which are not associated. You can see that there is no such significant unconformity over here. And the facies change, as I have explained to you, that the seal rock may juxtapose with the reservoir rock, and in the other case the pinch out may get truncated in this impermeable strata. Similarly, the buried depositional relief, you can see that here the carbonate reefs, they are providing a classic example of potential traps associated with buried depositional relief. They have already been buried, and then they are overlain by the younger sediments. Similarly, the aeolian dunes and submarine fan lobes, once they are already formed, they are older structures, and they are overlain by the new uh, uh, impermeable younger strata. So that traps the hydrocarbon over there. Then what are those which are associated with unconformities? As I had told you, there could be supra unconformity and sub unconformity. So once they are sub unconformity, that is beneath the unconformity, you may find truncation of tilted strata. So this is a tilted strata, they may truncate at the unconformity. So this is one type of trap. Then you may have sub-unconformity truncation associated with incised valleys. You know, the valleys which are incised by the sediment flows or the previously existing river valleys, they may form the traps below the unconformity surface. So this trap requires that the fill of incised valley forms part of the necessary lateral seal. Remember always that the oil has the potential to migrate anywhere. So if it is being formed over here, the laterally adjacent strata, this strata and this strata must be an impermeable seal. Otherwise, it may again go away. And then the buried landform. So it is a hill which is buried. Over it, the sediments are now being deposited, and then it may also form a potential uh, trap associated with the unconformity. All these are sub-unconformity structures. Sub-unconformity, below the unconformity, beneath the unconformity. And the supra-unconformity, above the unconformity, we have the on-lap. So this is the unconformity structure. You can see on lap means it is coming over here. This strata is lapping on the unconformity. This is one type of stratigraphic trap. Then you have let us say that this structure is incised valley, and then here the deposition occurs, and then it is above the unconformity. So it is reservoir deposition within the incised valleys or canyons. and onlap of buried topography. So this was some hill structure, hill-like structure, or any kind of upward raised structure, convex structure, and on that this reservoir rock has onlapped. So these are the supra unconformity traps, supra unconformity traps. So all these are very commonly found stratigraphic traps that are looked after for finding the hydrocarbons. What are the secondary stratigraphic traps? So the previous one was that we saw, it was about the deposition of the sediments above or below the unconformity and the structures associated. Now, when we talk about the secondary stratigraphic traps, they result from post-depositional alteration of strata. Alteration of strata means here the diagenetic changes start to happen. So they may either create reservoir quality rocks. So, say for example, there is a carbonate rock which is very tight, very tightly packed. It has no porosity and permeability. So the alteration of this carbonate may lead to the formation of secondary porosity, and it may cause the same reservoir, same rock to become a reservoir. Or there is a previously existing reservoir which is sealed by the alteration of the strata, and it may lose its porosity and permeability. So a previously existing non-reservoir can become a reservoir, and a previously existing reservoir may become a non-reservoir. So these are the post-depositional alteration of strata. So here you can see there could be a porosity permeability loss by cementation. There could be a porosity permeability loss, or sorry, enhancement by dolomitization or alteration. So all these could be, you know, it can cause the formation or loss of the reservoir. So these are also the secondary stratigraphic traps. So once a previously existing non-reservoir, it becomes a it becomes a reservoir, it need to be trapped by the you know uh, lateral lithology, so that the oil may get trapped over here. And if it is a previously existing reservoir and its porosity suddenly gets lost by cementation, then again the oil is trapped. So basically the work of the trap is to arrest or to stop the oil from migrating, and any such process which leads to the formation of a barrier which stops the migration of oil, it is called as a trap. So in the secondary stratigraphic trap, there could be a porosity enhancement by dolomitization or alteration, or there could be a porosity loss by the cementation. So the porosity enhancement associated with dolomitization and dissolution can create traps on its own, and therefore these are now suddenly changing the lithology, and therefore we call them as secondary stratigraphic traps. Mind you, here no tectonics is involved, therefore they cannot be called as structural traps. So I hope this things gets clear. And the third type is the hydrodynamic trap. So I had just explained to you that as the oil starts to move up dip and the water starts going down dip, it does not allow the oil to migrate further, as it is denser than the oil, and it stop its movement. So I hope these things get clear to you, and please go through this video very sincerely, so that these questions are commonly asked in the GSI exams, you may able to answer.